Our bodies have an incredible ability to heal themselves. But have you ever wondered how do they know when to stop? Scientists observed something fascinating about liver transplants. The donor liver doesn't just survive, it actually grows back to the exact same size as it was before. As the donor liver is cut, the surviving cells proliferate to cover up the lost tissue. But how does the liver settle to the exact same weight as before? What tells these hepatocytes to stop dividing once the liver reaches the previous size? Inside the liver, millions of hepatocytes perform a wide range of functions. These cells constantly monitor the amount of workload imposed on them. If some cells are lost, the remaining ones face more workload. This extra demand acts as a signal telling them to divide and replace what's missing. As new cells are added, the workload per cell drops back to normal, and that balance tells the liver to stop regenerating. This feedback system keeps the liver perfectly sized and functional, no more, no less. This kind of control doesn't happen only in the liver. Every tissue in the body uses a similar logic. To understand how this happens, let's look closely at what goes on when a tissue is injured. Every cell has an internal framework called the cytoskeleton, made up of thin protein filaments that give it shape and strength. The extracellular matrix located around the cells form a supportive network of proteins that gives overall structure to the tissue. This matrix is loaded with inactive growth factors. Whenever this network is damaged, these inactive growth factors become active and flood into the cells, triggering cellular proliferation. Cells maintain connections with their neighboring cells through proteins called cadherins, and these cells connect to their surrounding extracellular matrix through proteins known as integrins. These connections allow cells to constantly sense their environment, how healthy the surrounding cells are, how tightly they are packed, how much tension they feel, and whether the tissue around them is intact or not. If this network is broken, the cells know they have to divide. When an injury occurs, these connections are suddenly broken. Cells that take direct damage open apart and leak their contents into the extracellular space. Some surrounding bystander cells may also get injured. Their survival depends on the extent of injury. If the damage is within the limits of repair, the cells undergo self-repair. If the damage is severe, they die. These leaked molecules act as strong signals of cell injury to nearby white blood cells patrolling in the blood vessels. Almost immediately, white blood cells begin to migrate to the injured site. This tissue reaction is known as inflammation. The goal of inflammation is to clear dead cells, fight invading microbes, and to repair the tissue. The white blood cells recognize the damage, release cytokines that attract more immune cells, and stimulate the growth of new blood vessels. Increased blood flow brings oxygen and nutrients, while immune cells remove dead tissue and destroy invading microbes. Once the debris is cleared and macrophages found nothing to clear from the wound, these cells switch from a pro-inflammatory to an anti-inflammatory mode. Now, instead of destroying, they start rebuilding. They release growth factors that signal nearby healthy cells to divide and replace the lost ones. Over the next few days, the wound environment changes completely. The inflammatory chemicals are lysed down, immune cells withdraw, and the tissue becomes calm. Now begins the regenerative phase. New cells divide and migrate to cover the wound, forming a fresh epithelial layer. These cells also secrete a new basement membrane, giving the tissue stability and structure. As the cells reconnect with their neighbors through cadherins and the matrix through integrins, something crucial happens. These physical contacts send stop signals to the nucleus. The cells understand that the barrier is restored and there is no more space to fill. This powerful control mechanism is known as contact inhibition, and it's what ensures the healing stops at the right time.